Have you ever thought about how exactly does a solution get created? How do we go from separate solute and solvent ultimately to a solution? Delving into the particle level will really help us understand the chemistry that's involved and help to explain something called the heat of solution. So by the end of this video, you will know that we say that solutions form in 3 steps, and you will know what those steps are. And we'll be able to interpret those steps to explain endothermic and exothermic heats of solution. So let's dig in. Okay, so if we say that a solution is homogeneous, all right, do we really understand what that means? Well, homogeneous means consistent composition throughout. Now, we've talked about before that we know water molecules, H2O, are oxygens that have single bonds to 2 hydrogens, and we have 2 lone pairs. Now, I don't expect us to remember, but this is a bent geometry. And if we would get less of a ball and stick kind of model, but what we end up getting is what looks like, if we turn it, a Mickey Mouse head. So, water molecules are often drawn like Mickey Mouse heads, where we know these are going to be our hydrogens and this is going to be our oxygen. Now, we have lone pairs of electrons here. So remember, water molecules are polar. This side is our more negative side because the electronegativity difference of oxygen versus hydrogen will cause the electron to spend more time around oxygen, but we also have the lone pairs. So by the default, this side of the molecule will get the partial positive charge. But we're going to show water molecules as being Mickey Mouse heads. All right, so we have, these water molecules moving around, exchanging places in a liquid state. But if there is a solute dissolved, if it is a solution, they are equally distributed. So, we just want to try to represent that as best as we can. All right. So hopefully if you would grab a sample here you get the same number of particles. But we need to understand this a little bit more to perfect this drawing, but also to answer, well, how do we get there? So we know that solutions are made of solute and solvent. So in the case of sodium chloride, or you know what, let's do sucrose. So if you look under slight magnification, sucrose are cubic crystals, where the sucrose molecules have a lot of organization. It's covalent, molecular, crystal, and solid. So we can imagine that our basic unit cell is going to be, the sucrose molecules. They're held by dipole-dipole forces and a little hydrogen bonding going on. But there's attraction. I mean, we say in a solid, right? The particle attraction is greater than the kinetic energy. So these crystals form because it's a lower energy state. Well, then, of course, we have our water molecules, and we know our water molecules are going to be showing hydrogen bonding between them. And here, the particle attraction is equal to the kinetic energy, right? All right. Well, how do we get from this to what we drew here? Well, wow, these molecules took a lot of time to really get the dipole-dipole and the hydrogen bonding, the intermolecular forces, really to be able to show themselves. Well, to get these two to intermingle, we're going to have to invest energy to break this attraction. So, now, we as human beings, we have really no idea what is the first step, but we understand to get from here to here, we need to break that attraction. So the particle attraction, I'm just going to represent that as PA of the solute, is broken. We know to break anything, it's going to require the investment of energy, the investment of heat, or the investment of energy. And we know that then will have a positive sign on whatever the value is on the joules of energy we've inputted. Well, we're going to have to do the same thing here. And so we could call this step 2, or we could call this step 1, and then step 2. It really doesn't matter. We just have to know there's 3 steps involved. Well, these guys are showing, of course, hydrogen bonding. So the particle attraction of the solvent has to be broken. And anything that is broken requires an input of energy. So this will require input. And if heat is in the form, heat is the form of energy, then it's endothermic. And that value will have a positive sign. All right. Well, 2 things govern why things happen in chemistry. We are either lowering energy or we're increasing disorder. Remember, we called disorder entropy before. Chaos, if you will. So when we look at everything around us and what happens in our world, from the chemistry perspective, it's either that the process is lowering the overall energy, so what we end up with is lower in energy than we start, or what we create has a higher degree of chaos than what we started with. Well, so far, we have to put in energy and put in energy. We're not doing this. So, that's where the 3rd step comes in. Why on earth would the solute break apart and go with the solvent? Well, there must be some kind of attraction between them. So we say our 3rd step, again, these have to be happening simultaneously, but we do as human beings kind of put them in some kind of a stepwise order. The particle attraction of the solute and the solvent is created. And whenever attraction is formed, energy is released. So this is exothermic. So we say that these are the steps of solution formation or the solvation process. So the steps of solvation or the steps of solution formation or formation of a solution. So what we're saying in quote-unquote step 1 is we're investing energy to separate the solute particles. Then, or simultaneous, or before, we input energy to separate solvent. Then these can go together. Otherwise, why on earth would we or could we get this? So there must be some kind of, energetics that is lowered by these guys coming together. Now, of course, if we are going from an organized solute crystal to having them exchange places in a solution, we're also increasing disorder. So creation of a solution most often is increasing chaos and most often is lowering energy. So the solution ends up at a lower energy than we started. If we make 2 solutions, if we dissolve sodium hydroxide in water, it is a physical change. We are just making a solution. We are not changing the chemical identity of this substance. Actually, it feels warm. The beaker, the test tube will feel warm. It is releasing heat. So we know that the overall process is exothermic. However, if we do the physical change of dissolving sodium thiosulfate in water, it feels cold. You can feel, oh my goodness, that it really is absorbing a lot of heat. So it absorbs heat. So we know that's endothermic. Okay, well, we just talked about that to form a solution, you first break apart the solute, you break apart the solvent, and then this happens. So our first step is endothermic, our second step is endothermic, and our third step is exothermic. So we know these three steps are happening to take us from separate, solute, and solvent to a solution. So how can following these same three steps be overall exothermic in one situation and endothermic in another situation? Well, if the value of step 1 plus the value of step 2, those are our endothermic, is greater than the value of step 3. So if we have to invest heat at a greater quantity than is released, then our heat of solution is going to be endothermic. What we have to invest is much more than we get out. Where if step 1 plus step 2 ends up being less than step 3, if we get out way more than we invested, then our heat of solution will be exothermic. An analogy might be this. Let's say that you're babysitting 2 kids, and within a half an hour, the kids go to sleep, and you check on them every once in a while. Wow, you didn't have to really invest much effort. And the parents come home, they had a great night out, and they were gone for 3 hours, and they give you $100. Wow, well, the payout much greater than what you had to actually invest as far as energy. Now, that's exothermic. The payout greater than what you had to actually give up. But what if those 2 kids, oh my goodness, just wouldn't go to sleep, and you had to make them a snack and some hot chocolate, read them 10 books, have maybe a tickle fight, maybe put a puzzle together. Oh, so when those parents come home, you are just exhausted. You have given so much energy and effort. And for the 3 hours, they give you $5. Well, the payout is not nearly as great as what you've invested. So the same 3 steps can happen, but in one circumstance end up lowering energy, and that's exothermic. Well, then why would endothermic happen at all? Well, again, we have that payout of chaos. So it must be, even though energetically it's not being lowered, we're creating more disorder. So hopefully we have a better idea of, okay, how do we go from separate solute and solvent to then a solution? I pray that this video showed us just some energetics, that it gave us good illustrations of how are we getting from separate solute and solvent to a solution, that it happens in 3 steps, and that sometimes those three steps overall can be exothermic or endothermic. That is a video on solution formation or the solvation process.